Hi everyone, Chérif Matta here, your host, and welcome to a new episode of Conversation with a Scientist. In fact, today we don't have one scientist, but two. Professor Dr. Rob Thacker from St. Mary's University and his graduate PhD student or PhD candidate, Fraser Smith. The topic today will be anything but small. Everything big. It will be macroscopic. We will be talking about the universe and galaxies and their formation and their evolution. So without further ado, I will just introduce my guests here. Professor Robert Thacker is at the summit of his career, while Fraser Smith is a very promising graduate student in his advanced in his PhD studies with Professor Thacker at the Department of Physics and Astronomy in St. Mary's University. Dr. Thacker is a former Canada Research Chair, Tier 2, and he has held the chair for 2 terms, consecutive terms. And for those who are not in Canada and do not know what that is, it is one of the most prestigious research chairs in the country, in Canada. Rob has been also affiliated with various universities in Canada, including in Canada and elsewhere, including University of Alberta, University of Western Ontario, Queen's University, McMaster University, University of California, Berkeley. He works on simulating, with the aid of supercomputers, the formation of large structure of the universe, mainly galaxy and galactic formation. Professor Thacker is the director of the Science Outreach Center at St. Mary's University. He served formerly as the president of the Canadian Astronomical Society, and he is currently a member of the board of the Royal Astronomical Society of Canada. And he has hundreds of hours of video interviews and lectures online and elsewhere, as he is extremely strongly engaged in the public dissemination of science to the general public. And we're really, really happy to have Robert with us today. Robert, I will say one more thing, if you allow me.
Please go ahead.
He has co-authored several papers. One of them was published in the Nature, which is the top science journal in science, in 2005, with the title Simulation of the Formation, Evolution and Clustering of Galaxies and Quasars. And that paper in Nature by Thacker and co-authors have collected so far more than 6,000 citations according to Google Scholar today. I turn to my other guest here, PhD candidate Fraser Smith, who is from Nova Scotia, where we are filming this episode here in Halifax. Fraser is a senior graduate student of Dr. Thacker, and he's expecting to finish his PhD, shall I say when, or like 2027 perhaps? Yeah.
Hopefully, yes.
Yeah, okay. And in 2021, Fraser completed his Bachelor with honors in mathematics from Mount St. Vincent University, with a minor in physics from the same university, working on the diffuse interstellar band, related but not quite the problem of today's episode, working under Professor Tina Harriott of mathematics and Professor Daniel Magis of both Mount St. Vincent and St. Mary's, in collaboration with Professor Lou Matha at City University of New York, Hunter College in New York. Then Fraser moved to work on galactic superstructure with Rob at St. Mary's. So, have I missed anything important?
If I can just say one thing, I've actually stepped down off the board of the RASC.
Okay.
Just to be clear, you can always star it out formally.
All right. Thank you, Robert, for the correction. Sorry, I said Robert. I think
That's
I'm
okay.
not supposed to say Rob.
No problem.
But before we continue, Rob, I was a bit puzzled. Why Canada has 2 astronomical societies? Sure. The Canadian Astronomical Society is one, and then the other, of which you were the president, and then the other one, the Royal Astronomical Society of Canada, of which you were board member.
Yeah, I'll try and summarize this as succinctly as I can, because it actually has a number of decades of story behind it. But really, if you look at when astronomy as a research field was growing in Canada, you're looking really in the 1920s, around that time, C.S. Chant, and so on. And so there was a lot of research that was done, but the relationship between the amateur side and the professional side there was a lot of overlap. And so for a number of years, there would nonetheless be professionals go and work with the American Astronomical Society, which has always had a professional bent to it, although they now do allow amateur members. And so over a period of time, it became more and more clear that for reasons related to getting expensive things built, that there was a definite room for the creation of a professional astronomy society in Canada. And this was particularly related to the fact that the professional astronomers were also involved in the International Astronomical
And that is the
Union.
Royal Astronomical Society. Right?
So the Royal Astronomical Society was the initial society that was formed, and now the Canadian Astronomical Society is the professional society.
Oh, it's the other way around.
It's
So the Royal Astronomical Society was the amateur one.
Well, it was everyone, I think, and it still should be considered everyone, right? Because if you go to the UK, their Royal Astronomical Society is everyone, right? And so, but the US had this sort of like American Astronomical Society, which was really focused quite heavily. There was Edmund Hale and so on, all of those people who were doing lots and lots of very serious research. And so getting those large facilities built is a challenge. And you need to talk to the government. You need to have to do, I won't say lobby, but that does happen, for your own interests in getting research done. And so around the late 1960s, there was a big project, and that basically didn't work out. And so at the end of that, there was a feeling that really the community needed a professional society. And so CASCA was formed in about 1971.
Mm-hmm. And you yourself, you started as an amateur astronomer, and then because this is the one field of science I'm aware of where the amateur members of the community have contributed a lot of fundamental discoveries. Unlike, for example, physics or chemistry, where you need extremely advanced equipment, but here you need careful observation of the sky. And
well, I think it's always been the case that amateur astronomers have really sort of like set this platform of awareness that informs society. And it's always been like that. And that's never changed. What did, I think, change for a while was the technology that was used. The professional area kind of diverged, right? But now I actually think things are coming back together again, because although as professional astronomers will still tend to use these huge, enormous telescopes, the overall technology package that's used is very similar to what you can spend a few $1,000s of and put in your back garden. And so there is now a situation where some of the best imaging, in my opinion, is actually done by amateurs, particularly of planetary imaging. There's an astronomer called Damien Peach. Although people might argue the professional amateur distinction kind of blurs at some level, but that's related to the fact that technologies now have brought everything back closer together.
Now, astronomy is a very old science, traceable to the old Egyptians and Chinese, and it's probably a very unfair question to ask, but I will ask it anyway. Can you summarize in your judgment the main milestone, the principal milestone in this science since the old days to today? In your opinion, what are the principal key points in the history of astronomy, and were there any real revolution in the sense of Thomas Kuhn, for example?
Do you want to jump in? I'll add a few things, because Kuhn's I have a few thoughts about as well.
Okay, sure. I mean, as you said, it goes way back. There's lots of evidence. Early Greek even. I'd say probably one of the big first milestones was Ptolemy. With the Ptolemaic universe, where we had that, the picture of the Earth being at the center of the universe and everything orbits around it. Then there was quite the revolution with Copernicus when they proposed that it's a heliocentric, where everything orbits around the sun. And then that was backed up by such amazing astronomers as Galileo and Tycho Brahe and Kepler, and so that's where a lot of the fundamentals came along. And
so I mean, I think there are sort of like a number of clear revolutions in the sort of Kuhnian term. But I think where astronomy has sort of gone beyond that is not only just the thoughts and the concepts, but also the equipment that we're using. And so I'm just going to throw it out there. I think one of the single biggest revolutions in astronomy is the digital computer.
Mm-hmm.
Seriously, because it's changed what we can do entirely. Like the things that we had to do by hand.
Does it compare with the invention of the telescope, for example?
Oh, people will joke that if you say to an astronomer, do you want a telescope or a computer? They'll take the computer every time, right? Because you can do so much with it, right? And it's really true that really, I mean, a telescope today is literally a camera. Right. And we're processing digitally the images that we take from that. I mean, people still do visual observing for kicks, but very few people are doing that in a research context. I mean, finding objects every now and again, yeah, sure. But nowadays, the computer has made such an impact. And it's similar in terms of improvements in precision, right, in the engineering have had a huge influence on what we've been able to do in astronomy as well. And so I think that is another fundamental revolution that's kind of important to the field, but not in the true Kuhnian sense of scientific revolutions.
When I was researching, thank you, Rob. When I was researching your background a little bit before this episode, I understand that you are simulating galactic formation using computers through computer modeling. Can you please tell us a little bit more and
Sure.
whether that has is related to your Nature paper that I cited at the beginning?
Oh, absolutely.
Yeah.
I mean, so the Nature paper you mentioned at the beginning, I should give credit to my colleague Volker Springel in Germany, who is the lead author of the paper. Volker is a fantastic scientist, literally one of the best scientists I know in this generation. But that paper has become such a landmark because we created a data set that we could literally give to other people. And it's the fact that other people have been able to use that data that has made the paper so popular, right? But at the end of the day, what we're trying to do when we simulate these things, we're solving equations, but we're solving equations on a grid. And when you have a 3D grid, you can actually represent that in a 3D space. You can literally visualize it. What does it look like? And when you have the material in space, we have this really freaky thing called dark matter that is 86% of the mass content of the universe.
86% of the mass of the universe.
As far as we know, yeah. And so it's out there. We see that things are influenced by more material that we can see. So the models suggest there is this certain percentage of dark matter out there. And then you have the stuff that you can see, that what we call the baryonic material, the atoms, not necessarily emitting light. They can be emitting radio waves, X-rays, and so on. So we have all of these different wavelengths that we can use to get information about the universe.
What sort of mathematics are you? You referred to solving certain equations, and
it's all partial differential equations.
But what is it, like classical physics equation, or is it?
Oh yes, very much.
Is it relativistically? Does it involve relativity in any form? Or?
Yeah, if you were to be pedantic, you would say, yes, it involves relativity, but we do it in a context that is essentially an approximation, right? So we're able to take all of the really complicated space-time structure and then create a Newtonian analog of that. It's really very accurate. It's not perfect. No one will argue that it is, but it's very accurate. And we can do the relativistic reconstructions, looking back in time on top of that. It's essentially because the universe is not evolving particularly rapidly.
So you calculate the forces and you propagate in time and you take care of the...
We literally calculate all of the forces at one time, move the clock a little bit, move everything forward, and then calculate the forces
snapshots.
Again. Yep.
It's a little bit like molecular dynamics, if I understand.
It's exactly like molecular
Right.
dynamics. And it's just an entirely different scale you're modeling.
But then how do you factor in the dark matter in this business?
Well,
like the dark matter, first of all, is a continuous, like it's as if it's a continuous background, right?
Right, sure.
Yeah.
So the way we treat it is actually, even though it's a continuous background, you have to discretize it in your simulation model. So we have what I'll call mass packets of dark matter, all of which are mutually interacting with one another, and you're calculating basically good old-fashioned Newtonian force laws on those. But you're going to need a very, very rapid solver to do that, and that's where most of the effort was put into the 1970s, 80s, 90s, maybe to the turn of the century, on producing faster and faster algorithms.
You're trying to model the development of galaxies from what? From dust, clouds, or from?
It's a combination of dark matter. Dark matter is really important because material is actively falling into the dark matter. It doesn't have any native pressure to it, so it's going to keep on collapsing. But it is what we call a relic field left over from the Big Bang, right? And so then the kind of calculations Fraser is doing, you'll have that there. And then on top of that, you'll have the stars, all of the gas as well. And so you have to do those calculations too to calculate the evolution of the gas, which is considerably more difficult than the dark matter, which is really just gravity.
I will ask a question on behalf of the audience and not on behalf of myself, because I am driven by curiosity myself. But some people are not driven by curiosity. They're driven more by practical applications or motivations. What would be the driver for such a study for the lay person out there?
I mean, a big motivation, of course, would be curiosity. It's just a fundamentally fascinating field. However, I mean, at the end of the day, learning how these complicated systems evolve and like formed, I mean, to me, I mean, it always tied back to the, human curiosity of like, where do we come from, right? Yeah. And so that is a big motivator, is where, the universe is made of all these galaxies. We live in a galaxy ourselves, and there's still so much to learn about like how these change over time and how they came to be in the first place. So there's always that, where did we come from question that we can kind of, poke and prod at with research.
Now, Rob, at the beginning, you invoked the scientific method. And of course, scientific method include the proposal of hypotheses and their testing. So how does this fit in your research? And what sort of hypotheses are you testing?
Yeah, I mean, I would say that hypothesis testing in my particular field is not at all like, say, biology, where you'll have a very specific hypothesis, you build the experimental design, and then you go and do it. And so we work much more on what I would call a discovery basis, right? And so the hypotheses you're really testing will be fairly simple ideas of, if we do this, I think something will do this. But it's rarely framed in a really rigorous way. And so there's a lot of science that's done in astrophysics that's much more discovery-based than it is hypothesis testing. You do have hypothesis testing, particularly when you have statistical arguments in the field. That happens a lot because basically if the statistics are going to resolve the problem, then you start with hypotheses. But a lot of the times you're actually finding out about phenomena. And so you're trying to find relationships that describe that phenomena. And for those times, it's not always easy to even write it down as a hypothesis in the first place, because your hypothesis is, I can model this particular phenomena a certain way, but I have to do the experiment to find out what that way is. And so when it comes to the sort of like true hypothesis testing, I think most of the time we do it in a very generic sense, right? We're saying, well, we think, for example, the presence of supermassive black holes will have a particular impact on the evolution of galaxies. Let's model it this way. Does that happen? And so the good news is, if it turns out that it doesn't quite happen that way, it happens another way, you can still publish the paper.
So what is the main discovery that you would say that came out of your group and your approach? And has it been accepted by the general community? Did you have to struggle to get your ideas through?
I'm known for doing early sort of papers in fields, and then I tend to move on to new things. I'm not someone who likes to really get down into the real details. There are people who are very, very good at that. I'm not. I'm very much about what's the idea, what can we do with it. So the thing that I did in my PhD, which is again one of my most cited papers now, is to actually show that we can form galaxies with a reasonable disk size. For reasons that are fairly complicated, there was a problem with creating galactic disks when I started coming into the field. And we came up with a particular method of representing the energy from stars exploding within the galaxies that allowed the galaxies to evolve in a more precise and accurate way.
Just a minute, I don't understand. So you're trying to explain why galaxies tend to be disk-like rather than sphere, let's say, or is that what I understand?
So
why galaxies tend to become flat, like our galaxy, for example?
Sure. I mean, literally, we've all seen the skater with their arms out and they pull them in and they spin up, right? That's conservation of angular momentum. It's a fundamental property of the universe. And you have exactly the same thing happening as galaxies start collapsing down. So over a period of time, even the smallest amount of rotation will start becoming a bigger amount of rotation. Right? And so by the time, if you're collapsing down several factors of 10 and so on, then you'll actually go to a system that's rotating quite a lot and has a specific axis of rotation. And so if on top of that, you have a system for dissipating all the other random motions, which gas does, the gas between stars, the interstellar medium will do that, then you'll create a situation in which you wind up with something spinning that's just flattened.
And is it true that the majority of galaxies are actually flat disk structures?
Well, I mean, as with people, galaxies come in all different shapes and sizes. I mean, there's a, at least how we currently understand it, a lot of the early galaxies were like more spherical, elliptical, and then they would form these more disky structures. And naturally, I can't remember the exact numbers, of course, but you'll find that like as the universe, aged and all that, we found more and more disk galaxies would evolve, and eventually they can become spherical themselves or maintain that disk if they're not disrupted, say, because throughout the universe, galaxies are always merging, and so the fact that a disk may survive such a violent event is not always, it doesn't always happen. So there's a good mix of galaxies, I would say.
I mean, Fraser's made a really important point. There's what we call hierarchical merging. Small galaxies merge with other small galaxies to form bigger galaxies. Those bigger galaxies.
Galactic clusters, is that it?
So yes, that is basically the sort of like really large scale version of hierarchical clustering. There's kind of clusters of clusters, but it's not really strong in the same way as a cluster of galaxies is. And so that's a really important thing. And so you're seeing constant changes in the morphology at different size scales. And that's one of the things that makes galaxies so incredible.
What I found incredible is that we're really looking at the past here, because these galaxies are like millions of light years away, right? So this light, like you're looking at, is really extremely old. Like some of them are near the beginnings of the universe itself, right?
Yeah.
It must blow your mind to even think of that kind of thought, right?
So one of my favorite things to do to anyone who's looking through the telescope at SMU is to point it at a very, very distant galaxy, right? And it will only be this smidge, right? It's all you'll really see. And so a lot of people, that's not very impressive. But then I say to them, that thing you're looking at is 1.7 billion light years away. The light from that has traveled for 1.7 billion years through the depths of space to end its journey in your eyeball. How amazing is that?
Just to add a little bit of flavor to that for the non-scientific inclined audience, is that at the speed of light, the circumference of the Earth at the equator is about 40,000 kilometers. And if that was a straight line, and you put 7.5 of those, the light would travel 7.5 times the diameter of the circumference of the Earth in 1 second. So imagine how many millions of years?
Oh, in that case, it's a billion. It's
billion
a
years.
quasar.
So 1,000 million years.
I mean, it's really before life on Earth.
It's
really
mind-boggling. It's like you can't even understand something like this. So that being said, I mean, for me, it's fascinating, but how do you sell this kind of research to a granting agency? Why would the taxpayer give you money in order to study something like this?
Okay, I think I better answer that because I've done a lot of this, right? And so with a granting council, it's normally not so difficult because they are literally put in place to distribute money. The people you have to convince for particularly big astronomy projects is the government itself, right? Because the astronomy projects now, we're talking billions of dollars, right? For the biggest. I mean, very recently we got into a 1.7 billion euro project. And so you have to talk to the government directly about that. It's never going to be something that's just, there's enough money in the NSERC budget for this, the National Science and Engineering Research Council. No, they would need additional money from the government for that. And so we literally do talk to MPs. I've briefed the Prime Minister's office on these projects, and it's something that I actually enjoy doing because what we do is truly incredible, right? To be able to look back into the past with these amazing pieces of technology that actually do create other things, right? I mean, we need to remember that discovery doesn't happen in a vacuum, right? These ideas get taken and used in other places. Even something as incredible as the engineering of an observatory dome, right, moving 50,000 tons without any kind of squeaking or rumbling, you would think that has many other applications. Well, it does, because you need it in theme park rides to keep vibration down. So we have relationships with engineering companies who then use all of the research and apply it elsewhere. So we can happily tell you many stories of how these things get spun off, but we always come back to what Fraser mentioned, and that's that we do this to find out about ourselves and our own history, because we are tied to the universe itself.
And I think this is in my opinion, this is the most important aspect, is to understand we're humans, we are thinking animals, and the way we understand the universe is so crucial for us as a species intellectually, in fact. So in my opinion.
Well, I mean, I always joke that it's the universe discovering itself.
Exactly. We are observers within the universe because we're part of it, right? We're stardust in a way. So, Galileo, and this is a favorite of mine, famously quoted to have said something to almost verbatim to the effect of mathematics is the language with which God has written the universe. And he's further quoted as that the universe cannot be read until we have learned the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometrical figures, without which means it is humanly impossible, and he says humanly impossible, to comprehend a single word of this universe. And 3 centuries and a half later, another giant of science by the name of Eugen Wigner, a Nobel laureate in physics, wrote a paper that is really mind-stimulating in 1960, titled On the Unreasonable Effectiveness of Mathematics in the Natural Science. And he concludes that paper by the following statement, and then I'll shut up and leave you.
No. Okay.
The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift. And then he said this, which we neither understand nor deserve.
Yep.
We should be grateful for it and hope that it will remain valid in future research, and that it will extend for better or for worse to our pleasure, even though perhaps almost to our bafflement, to wide branches of learning. So what thought of mathematics is behind your computer simulation of galactic formation? Do you agree with these statements? What is your take on that? Why mathematics works so well? And I'll leave it to you.
So I'm going to let Fraser answer this, because I think I'm curious to see what he thinks as someone who's sort of like building their research career in the field.
I agree very much with, that mathematics is the language of our universe, and that you do need a good understanding of mathematics in order to understand everything. I mean, that was one of the great things about studying mathematics, not only just for the beauty of mathematics itself, but to realize that you can apply it in so many different ways. And so, I completely agree that it's baffling that it just basically almost by coincidence that we can explain our universe so well with mathematics. I mean,
by coincidence, you say?
Yeah, by coincidence.
Yeah.
I mean, there is applied mathematics where, we like statistics or
your degree is in mathematics primarily, right?
Right.
You started as a mathematician, but now you're discovering the galaxies using your mathematical skills. Yeah.
Right. And I mean, going through my undergraduate degree, that basically my thought process was that, it'll serve me well no matter what science I decide to do, just because it, as said, it is the language of it. And yeah, just the sheer fact that, like, yes, you can apply mathematics to this, but these mathematical principles also just exist on their own, and it's just there's a whole different beauty to it in and of itself just to study mathematics.
I mean, I have a hard time separating the fact that when you look at the basis of mathematics and the axiomatic structures we've created, those are fed in from the real world, right? So I think that it's not an accident that mathematics describes the real world, because the real world has a fundamental influence on it, at least for humans to develop it in the first place. And there are some people who take that concept a very long way, like Paul Davies, Arizona State University, and so on. I mean, for me, I think it's just a function of us trying to understand the world around us. Now, you can go into this very deeply and start talking about consciousness and what that means. Is mathematics discovered? Is it created? And so on. I have to be honest and said, why I thought a lot about that in my 20s. Now I spend more time doing mathematics. And so it's an amazing thought that we literally have this tool that exists within the universe and seems to explain it to such a high degree of precision. For me, I have a very pragmatic view on that. I think that if it literally wasn't good, we would try and come up with something that was better. So the example I will give is geometry is an incredibly powerful tool, but if we didn't have algebra, geometry would have eventually been limited to a certain extent, right? And so thankfully we have algebra, and so that allows us to go on and solve systems that are difficult to solve via geometric methods.
By abstracting the geometrical concept.
So that is, there are certain limitations to mathematics, and some people feel that there's no limitations to mathematics, but we may be hitting one right now, right? In this creation of this super theory of what the universe is, right? And it may be that there isn't a mathematical approach to describing that, but we don't know, of course, right? And so I think we have to be careful, because it's a difficult philosophical discussion, and you can easily make assumptions that may not actually have any basis. So although I thought a lot about this many years ago, now I tend to try and stay
You're more grounded on Earth, let's say.
I'm much older than I was back then.
Yeah. All right. So where are you two taking your research further? Maybe we'll start with the early career person, and then we'll go for the senior one.
So right now, just we're extending the research of basically we're looking at how galaxies, how individual galaxies compare to groups of galaxies, like how closely we can draw conclusions from groups and apply it to individual galaxies. And now that we've basically laid out the groundwork for that with the initial study, I'm very excited to start applying these concepts in study to more and more galaxies, and like with more complicated physics, and branch out as much as we can. And then basically after that, as far as like career research after PhD,
where are you headed after once you've done your PhD? Are you going for
I'm curious to know the answer to that too.
postdoctoral fellowship? What kind of direction do you feel? What is your view of your path forward from that point?
So, I mean, of course, it's on my mind a lot. I mean, it is a big decision. So, back during the master's degree, it's like, oh, make your 5-year plan, and now it's more so a 3-year plan now that we're approaching the end, because my plan was get the PhD and go from there. So, as it stands right now, I believe I would like to apply for a postdoctoral fellowship and do some postdoctoral
in
research.
Astronomy or astrophysics, right?
Preferably, yes.
Yeah.
The reason I started astronomy was I thought not only is it just fascinating to learn, but I found it just this perfect mix of mathematics, physics, chemistry, all these different subjects wrapped into one nice package. But after that, perhaps I might be able to apply to some university after some postdoc work, and maybe apply for some professorship or something. Mm-hmm.
Yeah, how about you, Rob? So where is your research going from here? I'm going to borrow
a great phrase from one of my colleagues who's just retired, and he said, we've reached the end of the beginning of understanding galaxy formation. And I think that's very true, because when I came into the field, we couldn't simulate things that looked like realistic galaxies. Now we can. Now the details really matter. And that might sound great, but it's also frustrating for me because I've always cut my teeth on problems that were really very general and widely applicable. And we're now getting into the specifics of things. And that's the field that I can work in that field, but it doesn't inspire me in quite the same way. And so I'm looking at a number of possible different things. I don't want to say what they are right now. But to Fraser's point that mathematics allows you to do so many things is very true. Like I've written interdisciplinary papers with my partner in environmental science. And so in terms of the simulation work, we've actually just started working with people from the Flatiron Institute in New York. They have
From what institute?
The Flatiron Institute. Mm-hmm. And so they have a very large series of simulations that they've done. And so it's probably the best suite in the field. And we have some ideas for things to do with that. So we had a conference call with them and they said, oh yeah, sure, we're happy to work with you on that. So we're just now starting that and we'll see where it goes. But retirement is in my headlights.
Well, Robert Thacker, Fraser Smith, thank you very much for being with us. And for the audience out there, I thank you very much for your attention and see you next time in the next episode of A Conversation with a Scientist. Thank you.